Okay, so we have 27 students, I think, from the class. So the first 7 are my students. So I will separate them into multiple groups. The first 7. And there are 2 PhD students. So I think they can be separated into the 8th and the 9th group. And we have 9 exchange students and 9 other students. So I think every group can have one, either my student or PhD, the other one exchange, and the third one is the third group. So it's a pretty good mix. So I will just randomly process the grouping right now. And if some of you drop the course, then your group will become 2 people. I think that's fine. And if all of your group members drops, you only have 1 person left, then you work on a very simple personal project, or maybe I will merge some of the groups later on. And if more students add in, I will just randomly assign to some of the group. So I will let you know who your group number. Okay, so let me just. So this is going to be this is a random sorting based on random number. So that's the result. I'm gonna paste them in this way. And then I'm going to do the same thing again here. Okay, so that's the order. Okay, so okay, so I don't need this anymore. And then I don't need this is this person. Anymore. Okay, let me do the sorting again. D. Okay. Okay. So, what did I do? I deleted the wrong, sorry. I know what I did. This should be here. Oh, so that's fine. I should copy these again down here, and then delete these rows. Okay, then do the sort. Okay. So here are the groups. Okay, so you need to know who's with who. So I will use this up this time to call up your name, to do a roll call, and if you're here, let me know. So 一拳, okay, and Giovanna, okay, 志文, okay, so you are group 1, okay, 易安, okay, and Giuseppe. Giuseppe. Oh, is there an easier way? No. Giuseppe. Okay. Giuseppe. I will forget about it next time. Giuseppe. Okay. 世君. Not here yet. Okay, so Ian and Giuseppe, you are group 2. Zixuan, okay, here. And Facundo. Okay. Facundo. Okay, Facundo, you are group 3. And Haojun. Okay, group 3. Okay. Qiuming is here. Okay. Lucas, easy one. Not here yet. Okay. Qiu Hu. Not here yet. Okay. Yihan. Okay. Here. Sao. Okay. Woquan. Okay. Is there? Okay. This is my student home. Not here yet. Okay. Matthias. Not yet. Chen Qi. Okay. Anyo. Okay. Rodrigo. Not here yet. Okay. Mizhi. Okay. And Xian Yifu. Okay, there. Okay, Louis. Not yet. Yongxiang. Not yet. Capiello. No. Federico. No. Boyuan. Okay. Okay, so this is current grouping. So today we have, okay, missing 9 students. I'm not sure if they will come or not. So we'll see. But at least this is the current grouping. You don't need to worry about this right now, because later on, the more courses we cover. So back to today's course. So last time we talked about the general format for optimization. And today we are going to cover unconstrained optimization. So basically, we only handle minimizing f of x. No constraint, no subject to. Okay? And I'm going to cover a very simple problem called the Newton's method. Okay? So what's happening is, if I try to make a drawing of this function in a one-dimensional space, it's like this. So this is your 1D design coordinate. X is your dimension. And of course, you have a second axis to show your function value. So we still treat this 2D figure as a 1D problem. Okay? The second dimension is for viewing the value of the function. So let's say I have a function that looks like this. Oops. Okay? So from the figure, you can tell this is the position. Because right here, you have the smallest function value. Right? But how do you find it? And if you make a guess, let's say here, and your function value would be this. Right? That's not the optimal. So the idea is, can we study how the function value changes with the change of your design variable? So by moving x a little bit, maybe for right, I will check again about the function value. See if the function value increase or decrease. In this case, if I take a small step for right, the function value will increase a little bit. So obviously, if I go for right, I will try to maximize the function value, which is not what I want. I want to minimize it. So this analysis of checking the change of the function value tells me I should go left. And from here, when you check the change of the function value, you are actually taking derivative. Right? If you move a little bit, I am exaggerating. If you just move a little bit, let's say this is delta. So here is function value at x0 plus delta. Right? And here is x0 plus delta. And what you did basically is the definition of taking a derivative. So you are actually taking derivatives to study so-called the sensitivity. Of the function. Okay? So there are something called sensitivity analysis. That actually means you are trying to study the derivative. If you increase x by a little, and if the function value increase as well, then you have like a positive sensitivity. And if you are on the other side, if your initial guess is right here, when you increase the x, function value actually drops. Then you have negative derivative. Okay? So it's an important step for unconstrained optimization methods. Most of those unconstrained optimization methods requires sensitivity analysis. Okay? So is the Newton's method. Okay? And what Newton did was, if I can study for the derivative, how about I make a polynomial approximation of the function. Okay, so this is like the first thing the mathematician did, try to figure out the direction of the function. To do further, you can make approximations. So let's try second ordered approximation of the function. And using with x k equals to 0 as the expansion point. So when I say expansion, you probably know what I'm going to do. We're going to do Taylor expansion. So actually, we're doing Taylor expansion. Because that's one way to make, a very easy way to make a second order approximation. Okay, it's a second order Taylor expansion. But you need an expansion point. Okay? So why do we do that? If you try to stay at this initial guessing point, and if you make a second order Taylor expansion, you try to approximate the shape of the function based on the derivative information right there. So you probably can get an approximate shape of the function, but the function may look like this. So this probably is your second order Taylor expansion. Taylor. The green one. So if you have a second order Taylor expansion looking like this, and if you can figure out what's the minimum point right there, that's a pretty good guess. So we will treat that one, the minimum point of the second order Taylor expansion, as your next searching point. So we will treat that this is the minimum point of the second order Taylor expansion. And we will treat it as the xk plus 1. So the idea is that you will try to use the derivative information to create second order Taylor expansion, and then later on I will let you know how you can find the minimum point of that second order Taylor expansion. Then do it again in the next iteration. So this xk plus 1 become the starting point of your next round of optimization. So in the next round, you will do it again. You will do the second order Taylor expansion again, and then you just hope eventually this movement will allow you to find the minimum point at some after several iterations. Okay, so that's the idea. Now, let's take a look why the second order approximation or the second order Taylor expansion requires derivative information. If you forget about Taylor, then I will remind you. And then take a look how you can get the minimum point of the second order Taylor expansion. So you can get xk plus 1. Okay? So sometimes when I write my notes, I may write something like this. This is with. Okay? And this is without. And this is because. Okay, and what is WRT? This is with respect to. Okay, so these are the more effective way to write those words. Okay, now, sorry. So let's try to do the second order Taylor expansion. Okay? With the expansion point. So sometimes you will write your expansion point as x0 or x something, but right now we are having xk, right, as expansion point. So this equation will be valid for any k iteration. So f of x equals to, approximately equals to f of x k. For short, I will remove the bracket on the superscript. So just xk. This is just easier for writing. Plus x minus xk times first order derivative xk plus 1/2 x minus k square times f second order xk, right? So this is your the second order Taylor expansion using xk as the expansion point, right? That's the approximation. So the goal is I try to find the minimum point. So we can only handle a problem that has the shape that is like coming down. So we call this kind of function, if I have a function like this is f and x, if it looks like this, so we call this kind of problem convex. So in Chinese, what does that mean? Convex means ao, so like a grooving into like a small groove like there. And if you have a different shape, then it's concave. So in Chinese, this is like two. So we can only handle convex problems because the minimum can be found. But for concave problems, the minimum goes to the negative infinity. You cannot find it. So we cannot solve concave problems. But so in our second order Taylor expansion, what kind of problem has this convex property? So the second order derivative has to be positive. So it's a convex problem. If the second order derivative is not positive, then you are basically solving a concave problem. And in optimization, in minimization, we can only handle convex problems. So if you see your second order derivative is negative, that means your gradient, this is called the gradient-based problem, cannot solve it. Newton's method cannot solve it. Okay, so if you find a problem that is convex, which means your second order derivative is positive, and where is your extreme value? Basically at the minimum. At the minimum, that's your extreme value. So probably in high school or undergrad or at some point of your engineering math or your calculus, maybe someone tell you that if you take a first derivative of the function and make it equals to 0, that can give you the extreme value. That's the location of the extreme value, because that's the location with 0 derivative. So take a look at the minimum point. That is an extreme point. And if you just focus on this point and take a look at the tangent of it, it's having a horizontal slope. That means right at this point, the first order derivative equals to 0. Okay, so we just, in order to find this point, we can just try to take the first order derivative of the function and make it 0. Then the solution of that equation probably leads us to the extreme point. So let's do that. The first order derivative of this Taylor expansion. So the first term disappears because it's a constant. And the second one becomes something like this. Right? And the other one becomes this. Right? This is the first order derivative with respect to x. Here is the only x. Here are the only x. Right? The rest of them are just coefficients, constant values in the function. Okay? So we want this to equals to 0. Okay? So let's just I made a mistake. This one. Right? This is the right one. Okay? So if we rearrange the function, you can see the equation can be written as right? So how about we just say the x is x k plus 1. So whatever solution you are having, whatever x you are having, the x must satisfy this equation, and that point basically is the extreme point, and that point basically is the minimum point of the function. So from now on, if I take a second order Taylor expansion of a function and then apply this equation, that means I am trying to get the minimum point of that second order Taylor expansion. So this is the equation for Newton's method. Okay, so all we need to do next is to do this iteratively. Okay, so now I'm going to write down so-called the solution process of Newton's method. The solution process. Okay, first you will have an initial guess x k equals to 0. At this point, iteration number k equals to 0, right? So you are going to make a guess, whatever x, okay? In order to perform Newton's method, I need two function values. One is the first order derivative at xk, and also I need second order derivative at xk. So you are going to evaluate these two function values, okay? And then you are going to apply the equation for Newton's method. Okay? And then you are going to do so-called a convergence check. So here I'm going to use one of the ways to check whether it's convergent or not. So I'm going to evaluate the difference between my new solution and my previous solution. So see if this difference is already small. So I can give a number, for example, 10 to the power of -3, if you think it's small enough. So it's like a question mark. You need to check whether the difference is small or not. So this is a process of checking. So usually you write it down in a diamond shape. Okay? And if not, just like last time, if not yet, you move back and the iteration number advanced by 1. If yes, then your optimal is your latest solution. So this is the solution process. Okay, so you take a guess. You apply this equation with the sensitivity analysis, the derivatives, first order and the second order. You check this so-called the convergence check. You check whether it's converged or not. If not yet, okay, just do it again. But when you move up, your iteration number increased by 1. If converged, okay, good. If the values satisfy this criteria, that means the new solution and the previous one is already very close to each other. So I think we can stop. We already found a pretty good solution. Then, yes, satisfying, okay, that's your solution. Okay, so that's the solution process of Newton's method. And this can solve unconstrained optimization problems, but only for one dimensional. From here you can see we don't have a second design variable, only x. There's no x1, x2, x3, only x. One variable, one function, no constraint. And this is only working when the problem is nicely convex. So the second order derivative has to be positive all the time. If sometimes the second order derivative becomes 0 or negative, then this will fail. Actually, not exactly the 0 one, because at the optimal, the second order derivative also equals to 0. But you don't want negative second order derivative. You don't want negative f double prime. Okay? Everyone okay with it? Okay. Any questions? Let's try to solve it by hand. So you can practice this solution process with me. Okay? Let's try to solve a problem. So let's say we are minimizing x2, x4 plus x squared. Okay, so this would be a function that has a positive f double prime all the time. Okay, let's try to solve this. So in order to continue, let me do f prime first. F prime basically equals to 8x cubed plus 2x, right? And f double prime equals to 24x squared plus 2, right? So from here you can see f double prime is always positive. So you're sure this function can be solved by Newton's method. Okay? So now if I try, of course we know the solution is 0, right? But let's say we're stupid. We don't know. So we just make a guess. Okay, let's try now k equals to 0. So x 0, let me make a guess of 2. Okay, so f prime of x 0 equals to, I need calculator. So 8 times 2 plus 2 times 2. So this would be 68 f double prime x 0 24 times 2 times 2 plus 2. So 98. Okay? So my x1 equals to x0, which is 2, minus 68 over 98. So 2 minus 68 over 98, that's a 1.306. Okay? I want to do convergence check. So x1 minus x0 equals 2. So 1.306 minus 2, that is negative 0.694 because of the absolute sign, so becoming positive. So this is still a large number, a large error. So not converged yet, right? So I will move on to k equals to k plus 1. So now k equals to 1. Repeat the whole process again. So I already know x1. x1 is right here. So what I need to do next is the f prime x1. So let me do it. 8 times. So I can write it down here. 8 times 1.306 cube plus 2, 1.306. Okay, this equals to cube plus 2 times 1.306. So this is 20.432. F double prime is 24 1.306 square plus 2. Okay, so 24 1.306 square plus 2. Okay, 42.935. So my x2 equals to x1. x1 is 1.306 minus 20.432 over 42.935. So this is equals to 0.830. Okay, so the difference between this one and the previous one is 830 minus 1.306, 0.476. So still not converged yet, right? So you will continue to do this until one day this error is small enough, then you stop. This is basically optimization. But in a research paper, you will never see this. They don't write it down for you. Okay, so it's a very fundamental mathematical process, but in quite advanced, like a solution procedure. Because if you have never taken a course like this, maybe you just don't know. It's not difficult, but you just don't know you need to do this exactly. Okay? And if we are programming for this, you just need to write a code that performs this automatically. So nowadays, if you using Python, MATLAB, or whatever software package that can do optimization for you, what usually happens is you need to tell the computer what's your function, and also you probably need to make a guess. And the computer code perform this for you. And sometimes it doesn't even tell you the detail. Okay, what's the function value? How many iterations it did? Yeah, usually it does. If you use a package like that, it doesn't do that. Okay, so this course basically teach you how to do that. Okay, any question? Okay, so I'm gonna do programming now. Okay. Let me try to enlarge the size. Okay. Is it larger? Do you see a change? No change, actually. So I need to here. Try this. Same size. Okay, it doesn't allow me to enlarge anymore, I guess. Is it still recording? Okay, still recording. Okay. It doesn't, I cannot enlarge it. So.
I think if you.
Oh, really?
Yeah. If you.
Do you hear?
Yeah. And maybe zoom in.
Ah?
Maybe,
Oh, yes. Okay, nice. Thank you. Okay, so in MATLAB, this is already a new script file. Okay, it's like a text file. So what I usually like to do in the first line, I like to say clear CLC and close all. Okay, so clear means you are going to clear the workspace. So if I say x equals to 1, in my workspace, I will have a design variable x in the space. So later on, if I design something and if my workspace is not clear, the value sometimes will be confused. Okay, so CLC means I'm gonna clear the command window. And close all means, because later on I would like to plot out some figures. So there will be some windows for the figures. To initialize the code, I would like to close all of them. Okay, so that's what I usually do. Now, we need to figure out how we are going to design a function. There are multiple ways for in MATLAB. I think I can use the symbolic. So if I say sims and small x, and if I say f equals to what was the or let me just create another one, 2 times x. I think that was the function, right? If I do that, So sims is for symbolic. And if I save it, if I save the file, and let me just say optimization. So let me run it. So once you run it, you will see. Can I also enlarge here? No. Okay, so on the left hand side, you can see there's a variable x in the class of symbolic, also a function of f, also in the class of symbolic. So how do you plug in numbers? If I say subs means substitute. Function f, and inside you plug in x equals to 1. So subs x1 basically means you plug in x equals to 1 into the function. Okay? So that's how you can plug in numbers. Okay? So we are going to have an initial guess. So for the purpose of keep tracking on all of my design variables in different iteration, I will use a different symbol. I will use capitalized X. So I will say big X equals to 2. Okay? And I'm going to have iteration number k, but in MATLAB, the index cannot be k equals to 0. So all the coding I'm doing here, the index number starts with 1. Okay? So you can even say this. Okay? My iteration number k equals to 1 and xk equals to 2. So that's my initial guess. Right? And I'm going to use a while loop for the coding. So when does the while loop perform this iterative process? It will perform this when my error number, the absolute error, is still large. So initially I can create some large number of error, just some random, just 100. Just for the while loop to operate in the initial. Okay? Then I will say while error is larger than 10 to the power of negative 3. When error is larger than my desired small value, then I will perform whatever that's written inside the while loop. So for every iteration, what I need to do is to compute for the first and second order derivatives at the current x. So I will call my first order derivative f as df. So it's diff. Diff will take a first order derivative of the function. So f comma x. ddf is my second order derivative. Okay? Simple? Okay? Then I need to do the Newton's method. How come AI knows what I'm going to do? AI is amazing. This is maybe AI know my database, or I don't know. This is almost exactly what I'm supposed to write. Okay, so xk plus 1 equals to the current one minus the first order derivative. So I will want to substitute the df and x using the current x. Let's plug in. Using the current function value, plugging into df. So whatever small x you are having inside df will be replaced by the current xk. Okay? And divided by this whole thing again, but ddf. Okay? Once you are done, your error is absolute value of the new one minus the old one. Okay? And before you get out of the error, the while loop, you need to advance your k by 1. AI knows what I'm doing. Okay? So, let's try it. And it took 9 iterations to complete. But without plotting out the result, we don't know what happened, right? So let's try to make some drawings. Initially, let's say plot f inside a region. So you can plot from -1 to 3. Okay? Not plot, easy plot. Easy plot is a function for plotting. It's a command for plotting a function. Easy plot. Obviously, they don't like easy plot anymore. F plot. I think it's fine. So let me see. Okay, so that's the function. Let me say hold on, because in MATLAB, if you plot something and when you plot something else, it will replace whatever you have plotted. So if you say hold on, whatever you are plotting will be stacking on top of the current drawing. Okay, so initially, I would like to plot a point, like a circle, at my evaluation point. So I'm gonna say plot at the current x, and then I need to plot right at the position on top of the curve. So I will substitute f and using the current x, right? And then I will plot it like a dot. So a dot means a dot. K means black. And I need this black dot to be large enough. So I'm gonna say marker size is called marker. So let's say 10. Okay, let's see how it looks like. So you can see this is my initial guess. Very small, so maybe 20. Okay? So initially, I made a guess at x equals to 2, and the function value equals to somewhere right there. Okay? And that's my function. Okay? So during the iteration process, whenever Newton's method finds a new x, I will plot the dot again at the new point. So let me copy this and place it here. But at the newer location, I'm plotting at the k plus 1. Okay, so that's everything. So you can see how Newton's method gradually moved to x equals to 0. And if you want to see some kind of animation, then you can say maybe pause by 0.1 second right here. Then you can see it's just too fast. Yeah, you can see it gradually moving on. Okay, so or there's I think you can try so-called a draw now. Draw now means don't perform the drawing and at least show me and then move on. Okay, I think it will. Yeah, at least it performs the draw now right here, and then you continue the code. So sometimes MATLAB is too smart. If you don't say draw now, it will perform all the drawing, then draw the whole thing once. So you will see a more efficient way of drawing. But anyway, draw now allows you to see, to catch your eyes. Okay, now what's also interesting is that how about the function values? So you can actually show text message of the solution process, right? So you can initially you can say display, and you can say new. Newton's method. It's not like this. Is it like this? No. I forget how to do it. Sorry. Yes, Newton's method. Okay. And then display means show a string of characters. Okay? And here I will display and say initial guess, and I will say k equals to whatever k you are having right now. So now it's a double, so number to string k, and then I want a bracket, a comma, and say x equals to, here again number to string xk. So this whole thing getting together as a huge, combined together into a long string. So what you are seeing here is, okay, Newton's method, initial guess, k equals to 1, x equals to 2. So if I change the value here, this string change automatically, right? And later on, during the optimization process, after I compute for the error, I will then display the current k. Yeah, the current k, that's fine. And then this will be x of the k plus 1, right? Or just say k equals to this. That's fine. So that's the current k, and then, so I guess right here I don't need to say this. I just say initial guess, k equals to something. Later on, k equals to 1. It's like the first iteration, and I get a new solution. So here is k plus 1, right? And I would like to show the value of the error. So we can observe how the error is gradually decreasing. So number to string error. Okay, that's all. Okay, right here, this is basically the solution process. Initial guess equals to 2, iteration from the first one until to 8. So we actually took 8 evaluations, 8 iterations. Although k equals to 9 at the end, but it actually took 8 times of the while loop. So every time x gradually decreases until it's becoming very close to 0, up to k equals to 7, the x equals to 1.1 times 10 to the power of negative 7, but still not converged. Because right here, the convergence criteria is the error between the current solution and the previous one. So we now, if you pick up your convergence check as the difference between current solution and the previous one, then it can only stop when you see error that is smaller than 10 to the power of negative 3. So it's a very strong criteria. You can see the solution is actually 1.2 times 10 to the power of negative 20. Very, very close to 0. Okay? So can I use a different convergence criteria? Actually, yes. So maybe I can evaluate f in a different way. Maybe I can say error equals to the difference between the function value. I don't want to use the difference between x anymore. If at this point my function value equals to 0.1, and if I move a little bit more, also 0.1. Why bother moving further? So maybe I can use a different way to define convergence. So I'm going to show you that secondary way. Okay, so right here I am plugging in, so substitute subs f x, okay, minus subs fx. So I'm checking the difference between the function value at k plus 1 and the function value at k. See what's the difference. Oh, it stopped. So why does it stop? Because when you are at 1 point something, the function, oh, no, something wrong. Because it's not numeric, so I have to make it a double. So, okay, because it was programmed as a symbolic function. So at the end, 7 iterations. Okay. So by different ways of deciding the convergence criteria, you may converge earlier or later. So which one is the right one? So none of them is, they're all right, they're all correct. So you are the designer. You tell people how you define the convergence criteria. And this is the result you get at the end. Okay, if you want a more accurate solution, you can try an even smaller convergence criteria. You can try different rules. Sometimes people also set up so-called the maximum iteration number. So in order to do that, you can say, an easy way is if k equals to 5, break. That's one easy way to set up an additional criteria if you say this. So we can do whatever, but I only have 5 chances for you. So don't do the 6th one. So that will be another way. But as a optimization designer, when you set up a rule like this, you need to write down, you need to tell people, okay, I set up a iteration maximum number. Okay? So let's get back to iPad. So what I did right there was here, this is the convergence criteria. Okay, so can also be right, or you can add another one. K has to be so if K in this way, so we usually put a question mark at the end. It's like making an ask question. Oh, is it satisfying? So right here, if I'm having a criteria right here, so I should say, is it greater than 5? If not, continue. If it equals to 5, okay, yes. Okay, so you can have, there are 3 different ways of stopping the process. You can even have combinations of some of them. So this is one criteria, another one, but you can have a mix of them. You want all of them to satisfy, then come out. So you can even can have or multiple criteria. Multiple of them, okay? So you are the designer, but you have to clearly mention how many criteria you chose in your code, okay? So up to now, any questions? If no question, I'm going to move on to second order, two-dimensional problem. Everyone okay? Okay, now. For multi-dimensional Newton's method. Okay? So what's happening is, now you are minimizing function of x, f of x, but your x now is a vector. So we are still doing the same thing. We are doing second order Taylor expansion. With xk as the expansion point. So right here you can see the xk now is a vector. Okay? So what does it look like? Okay, it's getting more complex. So what's happening is, this is the gradient vector. Okay, this whole thing. Gradient vector, or gradient vector, but you plug in at xk, right? And this guy is called the Hessian matrix. Okay, and all these are dot products. Okay, so now I'm gonna remind you what's inside a gradient vector and what is a Hessian matrix. So a gradient vector looks like this. Let me use M. Or let me just do this. So it's a n-dimensional. So they are now partial derivative. Partial derivatives. Okay? So you can write it in a different way. Sometimes people write it in this way. Do you know what is a EI? It's like a normal basis. What is a normal basis? It's like this. 1, 0, 0, 0, 1, 0, normal basis. You guys know, right? The normal unit normal vector that is parallel to all the axes. Okay, so sometimes people, you must have seen this. 2, 3, 4 can be written as 2i plus 3j plus 4k, right? ijk. But you can write it as E1, E2, E3. You can also write it as all the numbers. You just need to specify, okay, A1, A2, A3 as 2, 3, and 4, right? So why do I do this? Because later on I'm going to do some derivation, and Einstein designed some math so you can calculate, perform this more effectively. So sometimes people, for Einstein, he will write it as AIEI. Einstein doesn't write down the summation sign, so it's called Einstein's summation notation or something like this. Einstein's notation. So basically, Einstein did a lot of math, but he just ignored all the summation sign. It's because his brain can read this. So whenever you see same index, that means you are going to do a sum on that particular index. So same index means sum on that index. So for here, sum on I, for whatever dimension you're having. Okay, so let me tell you more about Bayesian. So Bayesian is a matrix. So it's gonna be second order derivative x1 square, x1, x2, da 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 da, da and then xn square. So a Bayesian matrix is a matrix that contains all the second order partial derivatives. So all the second order partial derivatives. Okay, and can be written as two summation sign right here. If I say I equals to 1 to n, j equals to 1 to n, so it's like this. And of course, for Einstein does this. So I and I, that means sum on I, and here J and J, sum on J. Okay? So what's the advantage of having this Einstein's notation? When you have dot product, let's say A dot B, if you write it as AIEI dot BJEJ, then this is a vector, this is a vector, this is a dot product that operates, that performs operation between vectors. So all these needs to be there in such a sequence, but the rest, AI and BJ, they are just scalar. And they are just scalar multiplying with each other. They can be reordered. So now you can reorder everything as AIBJ, EI dot EJ. Okay, so you come up with something like this. Okay, so what is EI dot EJ? So if you think of this as a three-dimensional problem. So 100 dot 100 equals to 1, but 100 dot 010 equals to 0. So EI and EJ vectors equals to 1 whenever I equals to j. Right? So EI dot EJ equals to 1 when I equals to j. But dot product actually is a sum of all these terms, right? So I should say no, it's not sum of it's basically this. Yes. So there is a delta being defined, so-called the Kronecker delta. Kronecker delta is being defined as 0 or 1, and Kronecker delta equals to 1 when I equals to j. And in other cases, it equals to 0. So EI dot EJ equals to Kronecker delta IJ because of the same definition. So if I can do that, then it becomes AIBJ Kronecker delta IJ. Okay, and there is a trick for a scalar. This is a scalar, and this is Kronecker delta. Kronecker delta. Kronecker delta always have two index. A scalar with some index times Kronecker delta with two index together, multiplying with each other, can be replaced as this, BI. So why BJ Kronecker delta IJ equals to BI? Why? Because Kronecker delta only equals to 1 when I equals to j. So BJ can only be BI when I equals to j. So Kronecker delta basically will swap the index of Bj by the other index. So here is a j, here is ij, so I can swap this j by the other index inside Kronecker delta. So that's at the end, this tells us A dot B equals to AIBI. What is AIBI? Basically, summation on I, right? So think about dot product. How do you compute dot product? A1, B1 plus A2, B2 plus A3, B3. Basically this. Right? This is exactly the same as how you learn about dot product. Okay? So why I'm doing this? Just for the later derivation. Okay. So if you are okay with this, now we can go back and take a look at these. So we now have to handle the troublesome part is this guy. Because later on we are going to take derivatives. So that guy is x okay. So later on when we try to take derivatives, when you are writing this in this form, is sometimes it's not easy. So what we need to do is we need to take first order derivative of this huge equation, this second order Taylor expansion. And what is the first order derivative of it? It's actually the gradient. So the gradient of f is gonna, let me copy the whole equation down here. So you it's easier for you. Let me copy this guy. Copy. Paste. Okay, and get rid of some of the things you don't need. Okay, we are going to do first order derivative of this, and we're going to make it 0. This is what we're trying to do. So what's happening is you actually can, let me see, do I handle term by term, or let me try to handle the whole thing together. So you will be doing this. Not here, just this. Okay, so first term disappeared. This is a constant, right? The other one right here, it's easy. Only thing left is the gradient. Only thing left is the gradient. So the troublesome part is the last one. So it's a half of the rest. Plus half of the front. How come half of these and half of these? Because you have a square term. You take a first order derivative with respect to this term first. So the coefficient is the rest in the back. And then plus you take a first order derivative with the last term right here. So the coefficient in the front will be left. Okay? But how do you put them together? Right here, you can think about this guy as some big matrix dot product with some vector. Let's use a small a. Okay, so it's like a Hij Eij dot Aijk. Let's avoid using k again. So Am, so Em, something like this. So the dot product between them can be written as Hij Am. They are the coefficients. They can be put together, and the rest will be Ei Ej dot Em. Right here, this guy can be rewritten as Kronecker delta Jm. Okay, and I can do swapping of these two because they have the same index j. So I can swap the j by m. So at the end, j being swapped by m, am. So that's the. So what does that mean? That means at the end you are doing summation on m, h, I, m, a, m. So it's like okay, h, I1, A1 plus I2, A2 plus da, 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 da. It's like you're doing something like this. So how about this guy here? at the end, at the third term. So the third term can be written as A dot H like this. So it's gonna be A M E M dot H I J E I E J. So it could be written as again H I J A M, but this time E M dot E I E J. So this is Kronecker delta M I, and I'm going to swap the I by M. So H M J A M. Okay? So they are very similar, but not exactly the same. So you can see this term ends up with this, and this term ends up with this. One is HIM, the other one is HMJ. And since we are in this particular equation, there's only one J, so I can rename it as a different index. It's okay to rename J by I, so this equals to HMI AM. It's okay, but I cannot swap the index. So over here you can see the first term, the purple term, is HIMAM, but the blue term is HMIAM. So this one is HIM, this one is HMI. They are not the same. However, Bayesian matrix has a special property. It's symmetric. So since Bayesian is symmetric, so what does it mean? HIM equals to HMI. Okay, can you explain this in human language? This means whatever inside when you have a HIM term, it's like you are doing second order derivative with respect to xi and with respect to xn, equals to doing this, swapping the order. Okay? Since this is happening, so this term equals to this term. They are the same. So I can put them together. Okay? Now, if I put them together, because of the symmetry, now the gradient f of x equals to gradient xk plus, I would like to write it in this way. I will write it this one. And I want this one to equals to 0, right?
Excuse me. I and J, you can replace it, rename it.
Yeah.
A little bit.
It's just a name. It's just a name.
Yeah.
So in this part, when you are deriving here, you're deriving some math right here, only for this term. I, J, K, N, those are just names for the index.
Yeah, but now,
So when I derive this, I can use I, J, and K. I can use I, J, and N. I can use any symbol.
yeah, but now they become identical. H, I, N,
Yeah.
and M, I.
So if at first, when I derive this,
But
because they are always representing the index that is not being swapped, and that index varies from 1 to n. So it's a number that goes from 1 to n.
yes, if I is never used in that equation.
Which one? This one? This one?
Yeah, yeah, yeah. Because I is used by other variable. It seems to be that you cannot use I anymore because it's already used by somebody. Yeah, you can use.
They are two different derivations. So it's like when you're handling derivation here, what you get at the end indicates that you have a summation of n because of the Newton's notation. So this is the result, summation HIN times AN. So n has, you need to do summation on n. You can do the same thing here. So that equals to, this equals to HMJAM, sum on m, right? But when you are having a formulation like this right here, it doesn't matter what's the name of it. It's just, yeah. So it's like a free index I or free index J.
Yeah, for that equation that is fine. But are they, we want to replace it to I, are they in the same system or they're totally different system? If they're different, then you can do
Okay,
it.
so, okay, let me think about it. So you're saying that in this particular equation, you are using I here, you're using J here. How can the IJ be the same one? Let me think about it. This is actually a vector. Okay, so if you write it in a index way, actually it's like a partial derivative with respect to I, EI, right? So in this whole thing, actually there are n equations. So whatever term you have a free index, that represent the particular one, the ith one. But no matter what name you're using, you can all call that the ith one here must sum with the ith one here, must sum with the ith one here. But when I do derivation here, the ith one, I can call it the jth one. It doesn't matter. So it's like, let's say we are looking at the third equation. So in this case, I equals to 3. Okay, I'm looking at the third term. I'm looking at the third one when I equals to 3. I'm looking at the jth one, but j equals to 2. They're just names. But all these ends up with I terms. I equals to 1 to n. They are I different equations.
So you're saying under the same I, the other one just name.
Yeah, they're just names.
Okay.
Okay? Okay. So, up to here. Now I want to rewrite this equation into the following form. I will have something like this. So this time I'm doing this slowly. Okay? And in order to move Haitian to the right-hand side, I will pre-multiply both sides of the equation with the inverse of Haitian. So at the end, I will have this. If I pre-multiply the inverse of Hessian, this become identity. So you don't need to write anything anymore. But when you pre-multiply H inverse on the left of the left-hand side as well, you end up with this, right? Then this gives me the Newton's method equation. That's the final equation. That's what we are looking for. So the general equation, when you are dealing with multi-dimensional problem, right here is not f prime over f double prime anymore. It is becoming the inverse of the Hessian equation, dot product with the gradient. So the gradient is a vector that is composed of all the partial derivatives. Hessian is a matrix that composed of all the second order partial derivatives. Remember to do inverse right here. So students sometimes forget to do inverse right here. So an inverse of a matrix is like a dividing in math. But you cannot divide a matrix. You can only do inverse. So it's an inverse of the Hessian pre-multiplying the gradient. Okay? So now I'm going to give you the complete solution process. You have initial gas, xk, now k equals to 0, right? And then you need to evaluate the Hessian matrix and the gradient vector. You can see how I am getting lazy. I use a superscript of k to represent plugging in the xk, okay? And then Newton's method. And then convergence check. I can compare the norm of my new solution and the previous solution to see if it's small enough, a question mark here. If not, k equals to k plus 1. And here is no. And if yes, then my optimal is the latest one. Okay, so let me draw the box. Okay. Here is the diamond. Check. That's the solution process. And you can see the difference is now you're dealing with multi-dimensional problem, and it's no longer simple derivative, it's a partial derivatives. And the Newton's equation becoming vectors. And when you do the difference between new solution and the old solution, because they are vectors, the only way to compare them is to do subtract and then calculate the length of the subtracting vector. So basically, so-called the norm, right? If you forget, it's called the norm. Okay? Any questions? Let's try to do it by hand, okay? Do I have time? Okay, still have a little time. So I'm gonna solve a much simpler problem, because if I solve a complex problem, very complex. So if I say something like this, okay? So the gradient looks like this: 4x1 minus 10, and here is 10x2. Here's the gradient. How about the Hessian? So divided by derivative with respect to x1 again. So 4, 0, 0, and 10. That's a Hessian, right? And what's the inverse of it? If you have simple problem like this, and if you have zeros on the off-diagonal terms, then the inverse is very easy. It's 1 over 4 and 1 over 10. But later on, if you solve a different problem when you have non-zero off-diagonal terms, you cannot just do this. It won't be the... You need to figure out a way to do inverse. Okay? Okay, now I have all these tools. All I need to do is just to solve it. So if I have an initial gas of 2 and 2, let's say 2 and 2. So let's try to solve it. My x1 equals to 2 and 2 minus my inverse, Hessian inverse, dot product with the gradient. So here 4 times 2 minus 10, 10 times 2. Okay, so you will see magically this is minus 2, and this is 20, and you will have 2 and 2 minus this is 0.5, and this is 2, right? So you end up with a vector. This is 1.5 and 0. Okay, so is it converged yet? Not yet, because if you compare with the current one and the previous one, obviously it will be some value higher than 10 to the power of negative 3, so not converged. So k equals to k plus 1 now equals to 1. So I will do it again. So x2 equals to x1. x1 is this guy minus my Hessian inverse dot product with gradient. So 4 times 1.5 minus 10. 10. Did I make a mistake? 2. Yes, you're right. Thank you. Yes, 2.5. So yes, so here is 0. So at the end you will see. So here is 2.5. Yep. So 2.5, 0 minus all these, and you can see it becomes 0 and 0. So at the end, same solution, and the difference between the new one and the previous one now equals to 0. So it's smaller than your criteria, so converged. So your optimal solution equals to the latest one, which is 2.5 and 0. Okay? It's looking much simpler because I'm giving you a simple problem. This is a second order polynomial with nice numbers. And the whole Newton's method is derived based on second order polynomial, Taylor expansion. So Newton's method is perfect for solving a problem like this because the derivation is based on the equation like this. That's why it can find the solution in one iteration. But n optimization always requires another iteration to confirm. So usually when you see solutions of iteration process, if you see the iteration number is only 1, most likely is wrong because unless you know the solution at the beginning. Otherwise, you usually start with something wrong. You did one thing, one iteration with whatever algorithm you're using, and then you need to confirm again at least one more time to see if the criteria satisfy. Okay. So, lastly, I will move on to MATLAB and then try to finish in time. Okay. So let me copy the whole thing and create a new one. So now I'm going to for 2D. So let me call it x1 and I have to do it quickly. Let me call it x1 and x2. So x1 square, x2 square, maybe minus 10 times x1. Okay. So now you need to decide your vectors. You want your vectors. Your vectors are vertical. So x vector has to be a vertical one. So I'm gonna call it 2 and 2, 2 and 5. It doesn't matter. So when you see this this sign there, that means it's a vertical one. So over here, it has to be later on. It has to be like this: column, comma k. So later on, when k equals to 2, it goes to the second column, right? Okay, and when you do plotting, now it's no longer a 1D problem. It's a 2D problem. So I'm doing contour. Okay, easy contour. I'm plotting within, let's say, -5 to 5 and -5 to 5, or maybe to 10. Okay, Newton's method. Okay, now it's you can only plot. You have to plot first one here. And then second one here. Okay, and then initial gas here. Now it has to be like this. It's a vector now, so I'm gonna add a bracket. Okay. So derivative part is different. So you will have x1 and x2, right? And for the Hessian, I'm gonna call it h. Okay. So for the Hessian, it's gonna be so diff again with respect to x1. Okay, and this one diff here x1 and x2. Okay, Okay, like this, second line. So let me copy these guys. So this should be 2 and 1, and 2 and 2, right? So here will be inverse, so H, this will perform inverse, times df. But you need to substitute in, subs H, x1, I need to do x1, x2, and then they are vertical. So current value is this guy. Yes. So substitute in H, and then after substitution, perform inverse. And here, let me call it G. G represents gradient. So substituting G. G. And this guy here. Blah, 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 blah. And here should be something like this. And if I'm doing everything right, I am plotting out the points. So here should be +1. And let's use the traditional one, the difference between the x. So now, not absolute, you need to use norm. Norm between the new one and the old one. And x now is a vector. Okay, no, do not need this line. Okay. Optimization. The second one. Okay, some mistake. What is the mistake? Initial guess. Number to string, it doesn't allow me to do this? Really? It's vertical, so I need to transpose it. It's some mistake here. I need to this is for plotting, to displaying the text. Because I'm always using vertical vectors, but string is horizontal. Okay, still something wrong. Okay. Here I need to make it a double because I am doing symbolic, but once it's solved, I need it being saved as numbers. Okay. No? What else? It doesn't need to convert, unable to convert expression symbolic into double, substitute. Okay, wrong. X1, X2. X1, X2. Okay, you see. Okay, got it. So, see, that's the initial guess somewhere. Here's 0 and 0. And here's my initial guess. What is this contour? This is the objective function. The warm color, the red color, represent higher function value. Cold color represent low function value. So I initially start from here, and I perform whatever Newton method asks me to do. Boom! I bump into like the center of the contour. Okay, and in the solution process, initially, I made a guess of 2 and 5. After first iteration, 2.5 and 0. Error was 5 point something. Another iteration, it confirms the same solution, so error goes to 0. the while loop confirms, okay, you can stop. Then that's the solution. Okay? So sorry, this part I was doing fast. The difference between the first code and the second code is that here I have two variables. So everything, because of the second variable, some codes need to become changed. For example, earlier it was an easy plotting a 1D function. Now I can only do contour. Okay, contour shows you like curves with the same values. And this is the initial position of the design variable, but I don't know the function value anymore. It doesn't plot out the function value. Okay, this is just true for display. And in the loop, gradient is a vector. It's a 2D problem, so this is partial derivative with respect to x1, and the other term at the bottom is the partial derivative with respect to x2, right? And this is Hazel. x1, x1, x2, 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 x1, x2, x2, right? Second order derivatives, 4 items. Now this one, original current cave x, Asian, plug in x1 and x2 using current value. After plug in, perform inverse times gradient. So substituting into gradient, and the rest is the same. Just replacing x1 and x2 inside the gradient by the current value, right? The rest are just for plotting. This is for plotting out the location of the new point, computing for the error, the norm between the two vectors, the new one and the old one, display the results. Continue to doing this until converge. Okay? Any question? I guess the only difficulty for you is that you're not familiar with gradient and Hessian partial derivatives because maybe you used it 2 years ago. So you're just a little bit forget about it. But now today is for you to get them back from your brain, right? And I did quite complex derivations on the multi-dimensional part just for easier. I don't need to write too many terms, but the concept is a little advanced. It's about Newton's notation, Kronecker delta. You have never heard of it. If you are in the field of solid mechanics, they use Newton's notation, Einstein's notation, and Kronecker delta a lot, because in solid mechanics there are a lot of summation terms. So they use it. If you are from that field, you probably feel okay. But here I just use it just for quicker derivation. Then I told you about the solution process for 1D and 2D Newton's method. I show you the diagram. Okay, start with initial guess, function value, Newton's equation, convergence check, and then perform the cycle, the loop. I did handwritten calculation for both problems in the notes. Okay, I recommend you to try hand calculation when you go back. In the exam, it's all about hand calculation. No computer allowed. You can bring your calculator, but you cannot just type in whatever, send to GPT, and then ask GPT to solve. I know GPT can do a good job, but if you are caught, that's considered as cheating. That's 0 points, right? You don't want that. So if you want to avoid that kind of issue, bring traditional calculator. Like, I don't know, Casio calculator. Bring that. So you don't have internet, you don't have AI to help you. Okay? Do hand calculation. Okay? So for the coding, I will send you both of the codes. They are simple codes. While I was coding for the first one, MATLAB AI already know what I'm doing. He even made a pretty good guess. When I was up to here, he already gave me Newton's method equation. So I guess in the world, when you calculate derivative and second order derivative, the next thing you do is Newton's method. So anyway, nowadays, coding are much easier. You can try your own coding at home. Try not to rely on AI too much. Try to do exactly what I did, line by line, and having a very clear mind about what you're doing, and then try it. AI can help you a little bit. If you forget what to do here and there, AI can teach you. And later on, when you are doing some projects, you definitely need to do some coding. So I will recommend you to do some practice when we still have learned just a little bit. So just gradually learn with the semester. Okay, so let me check whoever was not here, whoever were late. Sijun is here? No. Lucas? No. Chou Fu, I don't know how to pronounce. Okay. Hong, not here. Hong, you're here. Okay. Matthias? No. Rodrigo? No. Louis? Yongxiang? Capiello? No. Federico? So, who didn't get roll call? Everyone get it? Okay. So that's it for today. If you want to know about the grouping, here's the grouping. Okay. You can come up here. Small characters. So you can come up and see who is who. Okay. They're small. You can come up. Okay. You don't need to do anything with your group member yet. Okay. But at least we did some grouping today. That's it for today. Thank you. Any questions?